let us now understand receiver, and then we will see the how channel can be modeled. So receiver, I am assuming that there is an optical concentrator which may have a gain of 1, and then there is a detector, and there is a preamplifier which amplifies the signal, and then it is given for further processing. So assuming this is the receiver collection area, then this is the photodiode area. Once you are using a concentrator, so A Rx J for the jth receiver is given by the total photodetector area, n square, which is the refractive index for the concentrator, and sine square psi c. Psi c is the FOV angle. So the power received by the jth receiver is responsivity into the power and this is the channel matrix Hij into Ti, I is equal to 1 to number of transmitters plus the noise part, noise in the jth receiver. So this is the signal part and this is the noise part. And this particular noise can be represented, remember when we were discussing about the photodiode, the noise was actually coming as 2EI into P in and the bandwidth. This was the power, input power, this was the bandwidth, and the current generated, and E was the charge. So on similar lines, this noise is actually contains two components. One, because of the signal to the jth receiver, and these are ambient, which is natural light, any other artificial light present in the room. So there will be interference or noise from these two contribution also. So this is the noise in the received signal, and P signal J, the signal power received at the jth receiver is given by this PLED. This is the channel matrix Hij component, and it is from I to N2 because it is getting contribution from all the transmitters into Ti. And P ambient, the power is actually some constant, xi ambient, into receiver area plus into 1 minus cos psi c, where psi c is the FOV of the receiver. So this is the contribution from the P ambient. This can also be modeled. And the receiver, on the receiver side, you get vector, which is R1 to RNR at different receivers. So our total power, this is the total power, total received power, is responsivity into PLED into HT. So these are two matrices. This is H is a channel matrix, and this is your transmit vector. This is your noise vector, because there are many receivers, so it will be a vector again. So this is the total received power. And N is, as I mentioned, this is a received vector. This is for the jth receiver, and this is for the NR receiver. So once you know the R, and H is known, it is assumed that H is known. I mean, you have found out the channel matrix by doing some experiments. So H is known, and once, depending upon what you get R, multiply with H of inverse, you get the estimate of the transmit vector. So this is how the receiver, you get the, your recovered data. But if you notice, because of the structure of this non-imaging lens, the matrix which you will get is actually ill-conditioned matrix, or it is not a full rank matrix. not a full rank matrix. For example, if you have, 1, 2, 3, and this is say 2, 4, 6, it is a rank deficient matrix, not a full rank matrix, because if you see the column here, it is just double, of each element here. So it is a ill-conditioned matrix or not a full rank matrix. For a full rank matrix, your rank of the matrix should be either equal to the rows or column or both of the matrix. So, but this is not the case when your receiver is in the center of the room or moving along the axis. So you will find that the matrix which is coming using this concept of non-imaging, that matrix is generally a ill-conditioned matrix, right? So once you have not a full rank matrix, and if you want to try to find out the inverse of it, it becomes a difficult area. So for finding out the inverse, the matrix should be a full rank. And so finding out H inverse, which I need for my for estimation of the transmitted signal. So this will pose a problem to me, because as the matrix for such a case is ill-conditioned or not a full rank matrix. So in order to do away with this problem, we work on something called image diversity optical MIMO. So if you see the image diversity optical MIMO, or imaging of diversity optical MIMO. So in this architecture, you have, suppose this is a room. This is a room, and these are, say, transmitters here. Then on the receiver side, I use a lens, which is a hemispherical lens. And below this, I have an array of detectors. So I have an array of detectors. So all the light coming from the source is imaged onto the receiver. So I'm getting light from all the transmitters. So the bandwidth which I calculate, it will not be dependent on the location of my receiver. In the earlier case, the bandwidth was depending upon the location of the receiver. Depending upon where I'm in the corner or in the middle, bandwidth was changing. But in this case, all the light is coming from the transmitter. So my bandwidth will not depend on the location of the transmitter. Although it is making the receiver very complex, because you require a lens here. This is an image lens you will require. And this is some bulky arrangement. But if you see here, in this case, the matrix which you get is actually nearly a full rank or conditioned matrix. And that is the main requirement of MIMO, so that you are able to find out H inverse easily. And there is no, the noise also does not get amplified. So that's the advantage of using imaging diversity optical MIMO. So just to briefly tell the operation of this, let me draw one more figure for better understanding. So this is the same room which we are considering. So this is, for example, say the lens structure which is here, and if I want to see the image of these, some particular transmitter which has, say, A, B, C, D, A, B, C, D. This is, say, one particular transmitter, and then it'll fall onto this. This will here. This will come here. This is a image lens, And when you see on the receiver, you will get something like this. And this is nothing but your, this is coming here, this is coming here, and this may be coming in this corner. So you will get, similar to A, B, C, D. What you will get is A will be imaged here, and C will be imaged here. Let me denote this is A prime, C prime, and this will be B prime and D prime. So this is how it is imaged here. So you require a large number of receivers, or they're sometimes called as pixels. So that makes the whole system bulky. And you also require a hemispherical lens, which is a wide FOV lens, so that you are able to image all the transmitters onto this, on this receiver. The whole idea is because I want to have a full rank matrix, and wherever I go, I have the contribution from all the transmitters. So this is the importance of imaging diversity optical MIMO. And if you see the image, the channel matrix, I'm referring this as H image. Earlier was non-imaging, this is imaging. So this is H image for Ij is given by Hij, Hi prime. So this Hi prime is similar to what we had discussed. Only thing, it is multiplied by a factor, Aij. So Hi prime, if I see, this is again the number of LEDs in that panel. Receive collection area, this is the distance. They're all represented with dash because this is a case of imaging diversity or imaging optical MIMO. And this is phi ik, cos phi ik, and then these are the conditions. So this is the channel impulse response, and Aij is defined as, Aij is the, total, the area falling on the jth detector as compared to the total area. So this Aij is defined in this way, and the H image for the image diversity is Hij into Hi prime. So this is how it is modeled. So this was about two MIMO systems, non-imaging and imaging. And we have found out how it has to be modeled and how do you recover data once you know the channel matrix. We will do some examples in subsequent lectures. So then the understanding will be better when we do some example. So regarding indoor channel, we have studied indoor channel, and we also studied different limitations of the indoor channel. For example, multipath dispersion. So there is no fading. This we know. Initially we discussed this, and of course there is no Doppler effect because the receiver is not moving at high speed, and moreover there is no change of frequency happening when the receiver is moving. So there is no Doppler effect and no fading, but you do have multipath dispersion because inside the room, that there are reflections and there is line of sight. This is a receiver, and there may be more number of reflections. So because of this different paths for different rays, it will result into dispersion, and which actually limits your data rate. And your data rate is actually, this is a fairly approximate formula that RB, the data rate should be less than 10 of tau, this is the RMS delay spread. And this is your transmitted data rate. So as long as this condition is satisfied, you will get this data rate. So multipath effect has an effect on delay spread, and accordingly your data rate will be affected. So this is one thing we need to control, right? So, and also it's a fairly deterministic channel. This channel is actually time invariant. The second issue is actually light emitting diode bandwidth limitation. The bandwidth of the LED, the commercial LEDs which are originally installed for illumination, have only limited bandwidth of the order of few megahertz. Whereas the requirement is to have high data rate to the user. So this actually what happens in LED, commercial LED, there is actually a blue LED, blue color LED, and then you have some phosphorus layer on top of it. And when the blue LED passes through the phosphorus layer, it gives you white light. This is yellow in color. This gives you white light, which is actually required for illumination. But the problem is that it has a slow response. So which basically reduces the modulation speed of the device. So instead, there is a different kind of LED which are called as RGB LEDs. So basically, there will be 3 elements giving different colors: red, green, and blue. And when they combine, there is no phosphorus needed now. So when they combine, it gives you white light, and each of them, can be used for modulation, and you can increase the speed. I mean, you can modulate R at different speed, G at different data rate, B at different data rate, and you can do some processing to get higher data rate, or use of WDM for getting higher data rate. So this is, and there are other ways of increasing the bandwidth of the LEDs. You can do some pre-equalization of the LED circuitry, pre-equalization. You can use pre-equalizer at the LED transmitter, pre-equalization at LED transmitter. One can use frequency domain equalization at the receiver. One can use MIMO technique, which we discussed earlier, for increasing. Or one can use a different type of modulation scheme, for example, multi-level modulation schemes, multi-level, which can increase the data rate. So there are different ways of increasing the response of the LED, which standalone has a limited frequency response. Multi-level modulation scheme. Also, we should know that signal distortion, because the LED characteristic, if you see, it is not linear. It is this kind of curve, S kind of curve. So once, if you have more constellation points in the system which you are trying to modulate, then there may be nonlinearity. And there may be some crosstalk among the constellation points because of this nonlinearity in the LED characteristic. And moreover, it has limited dynamic range. So this is also limited. So you have nonlinearity in the characteristic. This is IV characteristic, IV. This is, you can say power, PV characteristic, voltage or control, voltage or current. So it is nonlinear. It may introduce some sort of crosstalk. And you have limited dynamic range. So in order to handle this, one can use, Volterra kind of distortion modeling, which is quite accurate. So if I use this kind of modeling, that is my power output of the LED is B0 plus B1 In minus IDC plus B2 In minus IDC whole square. So if I use this kind of modeling, which IDC is the threshold current, and this is the input current, And these are the polynomial coefficients. B0, Bi's are the polynomial coefficients. And so this gives a good fit to handle this nonlinearity. And if I use this Volterra, so one can get some advantage in terms of performance and in terms of modulation. So this is one way of handling the signal distortion, which comes because of LED's nonlinearity and limited dynamic range. The other issue which we should worry in such systems is, ambient light interference. This can also be modeled as white Gaussian noise. So if I find out the one-sided power spectral density, N0 will be 2E into IB, where IB is the current which is coming from ambient light sources. Could be natural, could be other sources which are not part of the communication. So this IB consists of these components, and this can be modeled as white Gaussian noise, which is 2E IB. So with this, we complete the discussion about the indoor channel, and we will also study in one of the lectures later how to simulate a indoor channel, and also we will study about one example for indoor channel, what kind of impulse response we get for some practical values. So these are the things we will do at subsequent lectures. And for the time being, we stop the discussion of indoor channel limitations at this stage. And in the next class, we will discuss how to model an outdoor channel. Thank you very much.